Welcome to our General Chemistry 2 class. For this video, we are going to discuss about thermochemistry. The objectives will be the following. Number 1, explain the first law of thermodynamics. 2, explain the enthalpy of a reaction. And 3, calculate the enthalpy of a given reaction using the Hess's law. Let's start with the definition of thermochemistry. Thermochemistry is a coined term. It came from two different concepts or words. Thermo means heat and chemistry, study of matter. Thermochemistry is the study that deals with the heat changes in chemical reactions. We have many different forms of energy, one of which is heat energy. Heat energy is the form of energy that flows between two objects because of their difference in temperature. When two objects in contact are of different temperatures, you expect the one with higher temperature to transfer heat from itself to the other of lower temperature until such moment that the temperature of both systems or objects are already similar or the same, and at that point thermal equilibrium is established. So it's always heat being transferred from the object that is warmer or higher temperature to the object that is colder and of lower temperature. Heat transfer. So it's not true that when you open the refrigerator, for example, or the freezer, or an air-conditioned room, na lalabas ang lamig, while in fact, it's heat that is traveling, that is transferring. Another form of energy is potential energy. This energy is possessed by an object by virtue of its position or chemical composition. So you will see here the biker at stationary position. According to its position and the chemical composition, it possesses potential energy. Kinetic energy, on the other hand, is the energy possessed by an object by virtue of its motion. So any object in motion possesses kinetic energy. So the bicycle being in motion here is possessing kinetic energy. Let's distinguish between system and surroundings. What is a system? A system is the specific part of the large universe that is of interest to us. And then the surroundings are the rest of the universe that is outside of the system. We have this illustration in consideration. The system includes the molecules that we want to study, which are the molecules of hydrogen and oxygen inside the cylinder. The surroundings are everything else in the picture, which include the cylinder and the piston. So the system is the chemicals or the substances inside the container. The container, the piston, and the rest of the um, um, surroundings or the rest of the materials are already considered the surrounding. We have three different systems. We have an open system as illustrated in A. In an open system, both mass and energy may be exchanged with the surroundings because of the open system, it allows exchange of both mass and energy. Whereas in the closed system, as illustrated in illustration B, closed system allows exchange of energy but not of mass. So if you are to compare the system A with system B or both, you will see that if the container contains water, for example, water vaporizes. So at certain temperature, water molecules escape through the opening, small opening here. The escape of water molecules will cause decrease in mass of the liquid or water. But if water is in the closed system, the vapor, the water escaping from the liquid state will not be able to escape from the system. So the mass is conserved. The mass remains the same in a closed system. Only energy may be exchanged. So since heat may be transferred, even if there is a wall between the system and the surrounding, heat may be transferred in or out of the system. So there may be exchange of energy, but not of mass. In an isolated system, um, neither mass or energy may be exchanged. So there is no possibility for exchange of energy and mass to be allowed in an isolated system. So these are the three. Let's talk about thermodynamics. Like the term thermochemistry, thermodynamics is also a coined term. It came from two different words or concepts. Thermodynamics deals with the scientific study of the interconversion of heat and other forms of energy. Since we have established in the previous slides that heat energy may be transferred, it's always from the warmer object to the colder object until a thermal equilibrium is established between the two systems. So the study of interconversion of heat to, let's say, mechanical energy or thermal energy or chemical energy or any other forms of energy, the interconversion of heat to other and other forms of energy is under thermodynamics. Let's first define the state of a system. State of system is defined by the values of all relevant macroscopic properties such as composition, energy, temperature, pressure, volume, and others. These are collectively called state functions. So to define state function, these are properties that are determined by the state of the system regardless of how that condition was achieved. State functions are those that can obtain initial and final states or conditions. For example, temperature. So an object may change from one temperature to another temperature. Let's say it absorbs energy or it releases energy. Pressure also, it may be increased or decreased with the system. So state functions are those that are characterized with either initial or final, or those that can obtain initial and final conditions. So regardless of how that condition was achieved by a system, they are considered state functions. What about the first law of thermodynamics? This is a form of the first law, the law of conservation of energy. In your junior high school, you have encountered the law of thermodynamics, the common statement, energy is neither created nor destroyed, because that is true. Under the first law of thermodynamics, the amount of energy in the universe is assumed constant. Yes, as a form of law of conservation of energy, first law of thermodynamics states that energy is neither created nor destroyed, that it can only be transformed or converted from one form to another. So, nagpapalit-palit lang ng form yung energy. So, as one object possesses a certain amount of energy, that amount of energy may be transferred to another body, or that form of energy may be transformed or converted to another form of energy. So see, with the assumption that the amount of energy in the universe is constant, we also assume that the amount of energy that energy forms are changing, that they are just transforming from one form to another, but energy is being conserved. Again, the total energy in the universe is constant. It's only converted from one form to another. So therefore, if one system loses energy, then we assume that the energy lost by that system is gained by the surrounding. On the other hand, that system may also absorb energy from the surrounding. That we will talk about more later. Meanwhile, let's take a look at these two illustrations. In the first illustration, we have, you can see the concept internal energy denoted by capital E. So in the initial state, there is a certain amount of energy. And then in the final state, there is a decrease in the internal energy. You will notice here the change in internal energy. Delta means change. Change in internal energy is equal to less than 0. So you expect this to be negative. Less than 0 means negative value of energy. As the energy of a system decreases, we assume that the energy is lost by the system. Where did that energy go then? Definitely, it is to the surrounding. So, as a system loses energy, the assumption is the lost energy is given off to the surrounding. On the other hand, the surrounding can absorbs that energy lost by one system. At the same time, energy may also transfer energy from to any system. So we have energy in the surrounding which can be given to a system or transferred to a system. So in that case, energy is lost by the surrounding and gained by the system. In the first scenario, it's energy lost by the system, lost to the surrounding. Internal energy, which is denoted by either capital E or capital U, means the total energy of a system. This is the sum of all kinetic and potential energies and of all components of a system. So if we have several components of the system, we get the sum of all the kinetic and potential energies of all these components for the total energy of that system. So we call that internal energy. In some books, capital U is used. In some books, capital E is used. Delta E means change in internal energy. Change in internal energy is computed as the difference between the final internal energy and the initial internal energy. So if there is change in the internal energy, for example, a system lost energy. So you expect that the internal energy of the system is decreased. So to get the change in the internal energy, you subtract the final internal energy and the initial internal energy. Again, delta E means change in the internal energy. E sub F, internal energy in the final state or condition. And E sub I for internal energy in the initial state or condition. Changes in internal energy may be positive or negative. So the positive or negative also have something to do with the type of heat exchange or heat change with the system or with the surrounding. If the change in internal energy is greater than 0, then the internal energy in the final state is also greater than the initial state. So if it's a system you are referring to and the amount of the internal energy in the final state is greater than zero, then you expect that system to absorb energy. Since nagkaroon nga siya ng increase in internal energy, ibig sabihin nun, nag-absorb siya ng energy from the surrounding. If that energy is in the form of heat, then we can illustrate that as given here, as illustrated here. Heat is coming from the surrounding and is being transferred to the system. In this case, the process is called endothermic, and you expect the change in internal energy to be greater than zero or any positive value depending on the amount of energy it absorbed from the system. So heat absorption is endothermic process. Endo means enter, into. It came from the concept into, meaning it in this case, heat is absorbed or is absorbed by the system or is transferred into the system from the surrounding. So in such cases, the process is endothermic and the change in internal energy is always greater than zero or any positive value. On the other hand, a system may also lose energy to the surroundings. So, ang opposite ng endothermic kanina is exothermic. Exo came from the concept exit, meaning lumabas from a system. So, in this case, from the system. If heat energy is taken from the system or is transferred from the system to another system or to the surrounding, the process is exothermic. And the value of internal energy, change in the internal energy, must be less than zero or any negative value. So what is the initial internal energy of the system? After losing energy to the surrounding, the internal energy of the final condition will be expectedly less kasi nga nag-lose siya ng heat energy. So that amount of heat energy by mathematical computation will be less than zero or negative. So in such cases, as energy is transferred from the system to the surrounding or are released given off by the system, the process is exothermic, and the change in the internal energy quantitatively is always less than zero or negative. Changes in internal energy. When energy is exchanged between the system and the surroundings, it is exchanged as either heat or work. So again, that energy that is either given off or released by the system or absorbed by the system, it's only either way, nag-absorb or nag-lose siya. That energy exchange may be in the form of heat so it's not always in the form of heat or work. So in another way, we can express mathematically change in internal energy in addition to the equation flashed in the previous slide. Change in internal energy is equal to the difference between the internal energy of the final condition minus the internal energy of the initial condition. So if the exchange is work or heat, then you can use or you can consider the equation change in internal energy is equal to the sum of the heat and the work. So this is heat lost by the system to the surroundings. So it will be the same as heat gained by the surrounding. Let's consider system. So in this case, using this illustration, to compute for the change in internal energy, Heat absorbed plus the work done by the system. Heat absorbed by the system plus the work done by the system is the change in internal energy. And that is always positive. So jibe lang din ito dun sa initial concept natin kanina na whenever a system absorbs energy, the value of the change in the internal energy is always greater than 0 or any positive value of energy. So in summation, heat may be transferred from the surrounding to a system. Positive Q means positive value of heat energy. Or heat may be transferred out from the system to the surroundings. In that case, the heat the heat quantity is negative, meaning that is lost by the system. In addition, with heat transfer into the system or towards the system, work may be done by the system. That's why to get the change, the change in the internal energy, you add the heat absorbed by the system and the work done by the system. Or work may be transferred out by the system. So it's just the same way. So it's always either absorbed or given off, or transferred in or transferred out, and it's always heat and work added to get the change in internal energy of a certain system, of a particular system. What about particularly in chemical reactions? To illustrate an endothermic or to represent an endothermic reaction, we have here energy plus 2 moles of mercury 2 oxide producing 2 moles of liquid mercury and gaseous molecular oxygen or oxygen gas. What does it mean having energy in the left side of the equation? This means that energy is absorbed by what system? By the system. So ito yung binanggit ko kanina, in the molecular level, ang after tayo yung mga substances involved in the reaction. So kung nasa isang container, ang system natin ay yung system ng chemicals or substances inside the container. The container, the cover, and the rest will serve as the surrounding. So our system here is 2 moles of mercury oxide. This means that energy is absorbed by mercury oxide. And absorption of heat by energy by mercury oxide results to formation of 2 products, 2 moles of mercury and 1 mole of oxygen gas. So this is an endothermic reaction because the system absorbed energy to produce the product. I mean the reactants utilized or absorbed energy in order to produce the 2 products. On the other hand, exothermic reaction involves release or giving off of energy. So in this case, you have 2 moles of hydrogen reacting with 1 mole of oxygen. So our system is the 2 substances as reactants and 1 substance as the product. The formation of 2 moles of water from 2 moles of hydrogen and 1 mole of oxygen. This reaction is accompanied by the release of energy. So this means that every 2 moles of hydrogen reacting with 1 mole of oxygen to produce 2 moles of water, there is a certain amount of heat energy being released. The greater the amount of the reactants producing water, the greater the amount of energy being released. So this reaction is an example of exothermic reaction because it involves release or giving off of energy. A thermochemical equation shows us the energy changes as well as the mass relationship. So it looks like a typical chemical reaction. So you see the chemical symbols and formulas of the substances involved in the reaction. In the left side, you have the reactants, and in the products, you see the reactants, and in the right side, you see the products. So to compute for the change in internal energy, you simply subtract the internal energy of the product because what we consider the final condition is the product, yung product side after the reaction na. As we said, internal energy being a state function obtains an initial and final states or conditions. So if it is a chemical reaction that we are considering as a system, then the reactants are do belong to the initial condition. The products belong to the final condition. So for this particular reaction, the final condition involves the product, sulfur dioxide. So what is the energy content or internal energy of the product? Having that subtracted from the energy content or internal energy of the reactants considered as the initial condition will be, so yung you do subtract the two, the difference will give you the change in internal energy of the system. As we said, the total energy in the universe is assumed constant. So there is always no net change kasi nagta-transform lang or nagta-transfer in and out lang from the system to the surrounding, from the system to the surrounding. So every time a system loses energy or heat energy to the surrounding absorbs that energy lost by the system. So it's always the amount of energy in the universe is constant, as stated in the first law of thermodynamics or the law. Let's go to another state function, enthalpy. Enthalpy is denoted by capital H, although in some cases it also means heat because it also means the same. Enthalpy is a thermodynamic function that is defined by the equation H equals E plus PV, where E means internal energy of the system and PV, pressure volume of the system. Since the three are all state functions, which depend on the initial and final states, as I have emphasized earlier, enthalpy is also a state function and with energy units. Change in enthalpy can be calculated using the equation change in internal energy plus the product of change in pressure volume product. Or if pressure is constant, you may use the equation change in enthalpy equals change in internal energy plus the product of pressure and change in volume. Take note that most chemical reactions occur at constant pressure. And at constant pressure, change in enthalpy is the heat gained or lost. So every time there's heat absorption or release, there is change in enthalpy, which can be calculated again by the given equation. Itong dalawang to. You can use either of the two depending. But since most chemical reactions occur at constant pressure, then in most cases you will be using the second equation for the change in enthalpy. What is enthalpy of a reaction? This is denoted by delta H. So delta H, enthalpy of reaction, is the difference between the enthalpies of the products and the enthalpies of the reactants. So earlier, we talked about internal energy. We assumed that there are internal energies for reactants and products. There are also enthalpies for reactants and products, and change in enthalpy, considering chemical reactions, can be taken or determined by the equation delta H, or enthalpy of reaction, or change in enthalpy of a reaction, equals the difference, ima-minus lang po, enthalpy of the products and enthalpy of the reactants. Parang internal energy din. You first substitute the enthalpy of the products and then have the enthalpy of the reactants subtracted from the enthalpy of the products. In an endothermic reaction, the enthalpy of reaction is always positive. That is, the value of the enthalpy is always greater than 0 or any positive value. Ulitin ko ang mga units natin ng energy. Internal energy, enthalpy, all these are energies. So the basic unit, the SI unit, joule, which can be expressed also as Newton meter, kilogram meter square per second square, or calorie or kilocalorie, depending on the problem or the situation. For every energy absorbed by the system, the change in the internal energy as well as the enthalpy is always greater than 0 or positive. For exothermic, since the system is releasing energy, the change in internal energy is always negative, meaning energy is lost by the system. If energy is absorbed, then there is increase in energy. If energy is lost by the system, there is decrease in energy. Therefore, decrease is denoted by negative value of enthalpy or internal energy. So for exothermic, internal energy, or rather enthalpy of the reaction is always negative or less than 0. What about enthalpy of formation? Enthalpy of formation is defined as the enthalpy change for the reaction in which a compound is made from its constituent elements in their elemental form. We have constant standard enthalpies of formation. We have here some substances, for example, carbon dioxide. The standard enthalpy of formation of carbon dioxide is negative 393.5 kilojoule per mole. Water, we have water vapor, we have methane, methanol, benzene, ammonia. I will be flashing this if there is a need for the constant enthalpies of formation. Let's have Hess's law. The law states that if a reaction is carried out in a number of steps, the enthalpy of the reaction, or for the overall reaction, is the sum of the enthalpy of reaction for each individual step. So kung ang formation halimbawa ng isang substance ay from a series of steps, the overall enthalpy of the reaction will be the sum of the enthalpies of the individual reactions. So isa-sum up lang yan, i-add up lang to get the sum. Although the enthalpy of reaction depends on the initial amount of enthalpy or the initial enthalpy. Let's have some examples. Forming water can occur in a single step or in a two-step. You will see here. Okay, let's have some examples. Forming carbon dioxide can occur in a single step or in a two-step process. The total enthalpy is the same no matter which path is followed. So we have here two steps. One is, so we have the reaction between carbon, solid carbon, and oxygen gas, forming initially carbon monoxide, and further combining, so carbon monoxide is the initial product. And then that is reacting further to a half bowl of oxygen gas, producing finally carbon dioxide. In the initial step, in step 1, the amount of energy lost by the initial reaction is amounting to negative 110.5 kilojoule. Why negative? As I said, for energy release or given off, amount of energy is denoted by negative value. In the second step, the enthalpy is negative 283 kilojoule. Adding the enthalpies of the individual steps, you will get a total of negative 393.5 kilojoule. So we have the sum of the enthalpies in the individual steps giving us the total enthalpy of the reaction. Okay, this reaction now involves two reactants, methane and oxygen, and two products, carbon dioxide and water. Because enthalpy of reaction is a state function, the total enthalpy change always depends only on the initial and final conditions. So if it's one step, the total amount of the reaction, or the enthalpy change of the reaction, is negative 890 kilojoule. So from the initial substances, methane and oxygen, to final substances or products, carbon dioxide and 2 moles of water, there is a release of 890 kilojoule. But you will see in these two steps different amounts of energy lost. So if it is a two-step, then there is an amount of energy lost in the initial step and another amount of energy lost in the second step. But again, the total amount of the energy, change in energy or energy lost or gain, is always dependent on the initial and final conditions. So in the first step, the formation of carbon monoxide and carbon monoxide from the reaction between methane and 2 moles of or oxygen, the lost energy is negative 607 kilojoule. In the second step, we have negative 283 joule. That is the further reaction of the initial product, carbon monoxide, with water and with oxygen rather, because water has been formed here. So carbon monoxide further reacts with water to form finally the final products. So again, regardless of the steps undertaken or taking place in the reaction, the change in enthalpy is always dependent on the initial state of the reactants and the final state of the product. The following are the thermochemical equations which may correspond to a chemical reaction. Like yung finlash ko po kanina, these are the representations. These are sample representations of the reactions. So we have negative 802 kilojoule, meaning energy is lost by the system. The formation of carbon dioxide and water is accompanied by loss of or release of negative 802 kilojoules. Same with the formation of liquid water from gaseous water. So this is condensation of water, vapor. That is accompanied by release of negative 88 kilojoule. The formation of carbon dioxide and water from methane and oxygen may also release amount of energy 890 kilojoule. So these are examples of thermochemical equations that you will see in books. So every time you see negative value of energy as delta H or change in enthalpy, that means heat is released or given off by the system, or the chemical reaction is accompanied with release of energy. Okay, let's have another example. So let's have this reaction. Propane reacting with 5 moles of oxygen, producing 3 moles of carbon dioxide and 4 moles of water. The diagram of the reaction is as follows. So notice 3 steps are involved. So imagining the reaction in 3 steps, we have the following individual reactions. The enthalpy of the reaction, the total enthalpy of the reaction is given here as negative 2,220 kilojoule. Hess law, we can compute for the enthalpy of the reaction using the equation, the summation of the enthalpy of the products minus the summation of the enthalpy of the reactants, but multiplied by their stoichiometric coefficients. So the italicized small letters N and M represent the stoichiometric coefficients. Those are the imaginary coefficient of propane, which is 1, 5 for oxygen, 3 for carbon dioxide, and 4 for water. So substituting the quantities, we have 3. So first, we substitute the energies of the products because the equation gives us the difference between the enthalpy of the products minus the enthalpy of the reactants. So in our equation, we write first the amounts of the products before the reactants. So for the products, we have 2. Carbon dioxide with coefficient 3. So we have 3 times the enthalpy of formation of carbon dioxide plus 4, coefficient 4 of water, times the enthalpy of formation of water minus the sum of enthalpy of formation of propane and 5 moles or 5 times the enthalpy of formation of oxygen. Substituting now the enthalpies of formation, you will need to take a look at the table that I flashed earlier in the previous slide. So you will need to take the enthalpies of formation from the table. So for carbon dioxide, we have negative 393.5. So we substitute that here and then multiply by the stoichiometric coefficient 3. That will give you negative 1,180.5 kilojoule. Add that with the product between 4, coefficient 4 of water times the enthalpy of formation of water from the table, that is negative 285.8 kilojoule. The product is negative 1,143.2 kilojoule. You will have that subtracted with the sum of the enthalpies of formation of your reactants. The 2 reactants are propane with no coefficient. So 1 times its enthalpy of formation is negative 103.85 plus 5 moles of water from the equation times the enthalpy of formation of oxygen is 0. So that will give you 0. So the sums will be negative, for the products, we have negative 2,323.7 kilojoule minus, for the reactants, we have negative 103.85 kilojoule. Having them subtracted, the final answer is the enthalpy of the reaction will be negative 2,219.9 kilo. This is also indicated in the diagram. So the net enthalpy of the reaction is amounting to negative 2,220 kilojoule. Negative the positive value of enthalpy for the first step because the composition of graphite requires absorption of heat. Heat is required to decompose graphite in the first place. The second step releases energy. The third as well releases energy. So adding all the enthalpies of the reaction, you will get the summation, the enthalpy of the reaction as 2,220 in whole number, kilojoules. And let's go to the last part, calorimetry. Calorimetry is the science of measurement of heat changes in physical and chemical processes. Calorimeter is the apparatus used for these purposes to determine the amount of heat changes involved in physical and processes. Let's distinguish between specific heat and heat capacity. Specific heat is denoted by small letter S. This gives us the amount of heat required or necessary to raise the temperature of specifically 1 gram of a substance by 1 degree Celsius. So 1 gram of water, for example, requires how many joule of energy to increase its temperature by 1 degree Celsius. So that's specific heat. And specific heat of substances are predetermined. So in this table, you will see the specific heat of some substances, including aluminum, gold, carbon in the form of graphite, diamond, copper, iron, mercury, water, and ethanol. So for water, the specific heat is 4.184 joule per gram degree Celsius. So what does it mean? 1 gram of water requires 4.184 joule to increase its temperature by 1 degree Celsius. Heat capacity, on the other hand, as denoted by capital C, is the amount of heat required to raise the temperature of a given quantity of a substance by 1 degree Celsius. For example, you are given 100 grams of water. What amount of heat is required or necessary to raise the temperature of 100 gram water by 1 degree Celsius? So be able to distinguish specific heat and heat capacity. Heat capacity may be determined by considering the following equations. Q means heat. So that is determined as the product of mass, specific heat, and change in temperature. Or heat capacity times change in temperature. Change in temperature is the difference between the final and initial temperature. Let's have some examples, easy examples. What is the heat capacity of 60 grams of water? So you are given here 60 grams of water. The question is, what amount of heat is required to raise the temperature of 60 grams of water by 1 degree Celsius? So earlier, we were given the following equations for heat capacity and heat change by a system. So you can use either of the two equations depending on the problem or the situation, where M means mass, C specific heat, C heat capacity, S specific heat, Q heat change or enthalpy, and delta T for change in temperature, that's final temperature minus temperature. So to solve this problem, of course, you have to identify the given. The only given here is 60 grams of water, that is mass of our substance. And then you can also list down as given, although it's not given here. You just are assumed to take a look at the table for the specific heat of the substance involved in the problem. The substance involved is water. So using the table in the previous slide, you will get the specific heat of that substance, water. And we have mentioned that it is 4.184 joule per gram degree Celsius. Substituting the given to our equation. So we make use of the equation specific heat equals the product of mass and heat capacity equals the product of mass of the substance and heat capacity of specific heat of that substance. C means heat capacity, S is specific heat, which are constants. Specific heat are constants. Heat capacities are to be computed according to amount of substance given. So in this case, you are given 60 grams as the amount of water. Water is the substance involved. What is the S or specific heat of water? That is from the table 4.184 joule per gram degrees Celsius. Canceling the similar units between numerator and denominator, you will have joule per degree Celsius left as the unit. So we took the specific heat of water from the table that I had flashed earlier. Multiplying 60 by 4.184 joule, you will get 251.05 joule. What does it mean? 60 grams of water will increase its temperature by 1 degree Celsius for every 251.05 joule energy absorbed. So for 60 grams of water to increase its temperature by 1 degree Celsius, it must absorb 251.05 heat energy. Another problem. 394 grams sample of water is heated to change temperature from 10.75 to 83.20 degrees Celsius. Calculate the amount of heat absorbed in kilojoule by the water. So, ang assumption natin ay nag-absorb siya ng water kasi tumaas yung temperature niya. That's a common notion. Pag uminit yung isang bagay, ang assumption natin ay nag-absorb siya ng heat. When a warm object becomes cooler, lumamig, ang assumption naman natin ay nag-lose siya ng energy. The question is, saan napunta yung energy lost by that object na lumamig? Edit to the surroundings, babalikan natin yung law of conservation of energy. Energy is neither created nor destroyed, but can be transformed from one form to another. Or, since it is an open system, energy may be transferred from the system to the surroundings. So, kung ang bagay ay mainit, lumamig siya, ibig sabihin yung heat content niya ay lost to the surroundings, na transfer out from the object to the surrounding. On the other hand, kung ang bagay naman ay malamig, galing siya sa ref, malamig. After 10 minutes, uminit na siya. Ang assumption naman dapat natin doon, yung object from low temperature, umakyat yung temperature niya because heat is being transferred from the surrounding to the cold object. Nagkaroon po ng transfer of heat from the surrounding to the object. And we always assume that the transfer of energy is always from a warmer or higher temperature to lower temperature because heat transfers from cooler to warmer object. So going back, since we need to calculate for the amount of heat absorbed or given off, we will have to make use of the equation heat absorbed or given off equals the product of mass of the substance, specific heat of the substance, and the change in temperature in the substance. So we are talking about what substance in our problem? Water, amounting to 394 grams, with initial temperature of 10.75 degrees Celsius. So ang tanong, what amount of energy has been absorbed by water in order that caused it to increase its temperature to 83.20 degrees Celsius? So substituting all the given quantities, we will have the given mass is 394 grams. The specific heat of that substance water is given earlier, 4.184 grams per gram degree Celsius. 72.45 degrees Celsius is the difference, the delta T. Delta T is final temperature, 83.20 degrees Celsius, minus initial, 10.75. That gives you 72.45 degrees Celsius. Canceling the units, similar units between numerator and denominator, gram, and denominator degrees Celsius, numerator degrees Celsius, you will have joule left as unit. Joule is a unit of heat. Heat is a form of energy. Regardless of the form of energy you are talking about involved in a situation, the unit remains to be any of the units that we have mentioned earlier, joule, Newton meter, any form of energy. Work is done with energy. No work is done with energy. The unit of work is the same as the unit of energy. Multiplying 394 by 4.184 by 72.45, the answer will be 119,433.54 joule. If in case you need to convert this to calorie or kilocalorie, you just make use of the conversion factor to cancel the unit joule and change it to calorie or kilocalorie depending on the required unit. So that concludes our lesson